We have just put together a whole, back again in the meeting. So we're going to continue the agenda. Item number 10 is the next presentation. Identifying potential drivers of change in seagrass and algal community composition in the aquatic reserve. This presentation will be given by Mike Wessel from Janicki Environmental. The purpose is the goal of this report is to provide analysis of changes in seagrass and algae community change over time and identify potential drivers of change in Charlotte Harbor and Estero Bay. The connection is the water quality improvement priority action number 1. Identify, study, and monitor new emerging pollutants and of concern and their potential drivers. So with Daniel there, we're gonna just listen to the presentation. Thank you very much. Mike, are you there?
Yes, Ernesto, I'm here. Thank you.
Thank you. Thank you very much. Go ahead and take it over.
Okay, I appreciate the introduction and the kind words. I'm sorry I can't be there in person. This is was kind of a last minute thing for me. So hopefully it goes as well as you said it might. But I appreciate the opportunity to look at this issue on seagrass. It's been really interesting to me to get into the Charlotte Harbor Aquatic Preserve and the Estero Bay Aquatic Preserve data. I just want to compliment those guys. They do a great job of collecting the data, very rigorous data set, well-organized data set, and it made my job easier in terms of doing the analysis. It is a challenge. There's a lot to it, and I'm not going to be able to get to all of it today, but there is the report is part of the TAC packet, and I appreciate any comments on that. Next slide, please. Yeah, so the goal was really to provide a unified analysis of changes in seagrass with a focus on identifying potential drivers in these changes over time throughout the entire study area, including the Charlotte Harbor complex and Estero Bay. It's a fairly large study area, and there has been some analysis done previously on that, but it hadn't been updated in a while, and it didn't cover the entire study area. So this was a way to take all of the data that have been collected throughout the entire study area and provide kind of like a unified framework for analyzing it. And that includes individual seagrass species, frequency and composition, abundance, the transect length, which I'll talk about, as well as a deep edge analysis of how deep the seagrasses grow, shoot counts, and associated macroalgae and epiphytic coverage to some extent. The next slide, please. This is a map of the study area, and each of those green dots represents a transect, a seagrass survey transect. And they're, as you can see, spread out from Lemon Bay all the way down to Estero Bay. It's a long, it's a large area to cover. The Charlotte Harbor Aquatic Preserve monitors 50 of these sites annually around September. The Estero Bay program has 5 sites within Estero Bay that they monitor twice a year. We're only going to be talking about their summer sampling season to keep it consistent with the Charlotte Harbor Aquatic Preserves. And then DEP has 3 transects in the Caloosahatchee River that they sample quarterly, as well as 3 sites that are also sampled by the Charlotte Harbor Aquatic Preserve. Again, we're only looking at the one-time summer annual assessment, just to keep everything standardized in that regard. When I talk about, sometimes I use the word transects, we also call them sites, and they are different from the stations within a site that I'll talk a little bit more about. But the sites were established generally in 1998, extend from a mangrove shoreline, typically out into open water along the compass bearing. And when they started out, they were recording individual seagrass species. And then in around 2004, they started recording a total Braun-Blanquet score, which I'll talk a little bit about, but it's an index score related to the percent occurrence or the percent coverage of seagrass within the quadrant. Next slide, please. So this is this is a method slide, and this the graphic on the right. And I could probably use a pointer. You can't see my pointer, I guess. If we're looking at the figure along the x-axis, this is a single transect as an example for MCO3, which is in the east wall. And so the plot along the horizontal axis is a transect. So it starts at 0 meters and goes out seaward. And in this case, a quadrat is laid every 50 meters along this transect that is actually over 600 meters in length. They vary in length throughout the study area, but at each station, at each, which would be each numeric value on the x-axis, there's a sample taken, and it's recorded as to what seagrass species occurs there and what percent coverage of that seagrass species there is. They also record not only the 4 major seagrass species, Halodule, Thalassia, Serengodium, and Rupia, but they also record Caulerpa and Halophila, as well as they will note if sargassum is present, and if the sample contains no seagrass, that will be recorded as no seagrass, which is represented by a black dot in these plots. So you can see along the x-axis, we have a transect for a particular year, and along the y-axis, we have the time series for a particular station within a transect. So if we look at the 0 station and we go vertically from 1998, we can see that at this particular station, we had Halodule beginning in the early part of the time series, and then it kind of we lost the Halodule, and it kind of started to transfer into more of a Thalassia driven station. And then it kind of varies back between Halodule and Thalassia. And you can also see kind of the middle of the transect in the more recent years where we've lost a lot of data. That's represented by the size of the bubble. So in the most recent years, we've lost quite a bit of coverage in the center of this particular transect. But that's just to give you a kind of an idea of the methodology that's being used and how we are looking at this data set. The individual species, Thalassia, Serengodium, Halodule, they represent a total Brun-Blanc index, and most of the actual analytical work was done on this total score. So it didn't matter what the species was, it would be percent coverage of any of the major seagrass species when we were analyzing those particular scores. Caulerpa is recorded, but not part of the total Brun-Blanc score. And drift algae is also given an abundance estimate separate from the total seagrass or total Brun-Blanc. You go to the next slide, please. To continue with the methods, the explanatory variables included flows and water quality and some covariates from the actual seagrass data, with the conceptual model being that flows would affect water quality, which would then affect seagrass data. And this plot is actually just a time series plot of the flows that are standardized to a long-term average so that we can kind of easily look and see which were drought years and which were surplus flow years. So this is for the Peace River. So we can see that around 2000, between 2000 and 2001, we had a severe, extensive drought, historic drought, and it was followed by some really supplemental flow years between 2003 and 2005. And then we had another pretty extensive, not quite as intensive, but extensive drought between 2007 and 2009-ish. And then we've gone to, in the most recent years, kind of an above average flows, but not extremely above average, but more consistently above average. So you'll see these plots in the report. They're kind of a way to just highlight the deviations from what are expected flows over the long term. Next slide, please. For an analytical approach, we defaulted to non-parametric methods for descriptive analysis and changes over time. We did that because the Blanc K-scores are actually discrete values. I didn't have room in one of my previous slides to show you the Blanc index. Some of you know it, some of you might not. I do have one next, but they're basically an index score between 0 and 5. So they're discrete values, so they lend themselves more towards non-parametric statistics as a default, but they're when it comes right down to doing modeling work, you kind of have to move towards a more parametric approach. So we did some PCA and ordination. We used seasonal Mann-Kendall for chess over time, and Spearman's rank correlations. Those are all non-parametric methods for some of the simple correlations. But we get into the statistical modeling, we get into more of a parametric setting, which I'll talk about a little bit later on. Next slide, please. So just to describe the data a little bit and just get right into it. Next slide, please. And I know this is hard to see probably in your presentation, but one of the first things I did was I used this heat map. So I took the percent, I normalized each of the percent occurrence values for each of the individual species, like Halodule on the very most left column. The vertical axis is all of the individual sites. And you can see that, well, let's see. Basically, the highest percent occurrence for Halodule would be given a 1, and every other percent occurrence for every other site would be a proportion to that 1. And so a red value means a high percent occurrence for Halodule. And then each of these individual metrics, Syringodium, Thalassia, we use depth, not only the mean depth, but also the 95th percentile of depth to look at like the deep edge. And then on the farthest right column is the total Blanc K-score. And really what I want, the takeaway from this heat map is if you look on the far right column, you'll see these values, these sites that had the highest total Blanc K-scores, which are red, also tended to have at least one or more than one individual seagrass species that was fairly frequently occurring. So the table on the right here shows the top 10 highest average Blanc K-scores. So GAS05 had the highest overall score, and it had 24% occurrence of Thalassia, 23% occurrence of Syringodium, and 50% occurrence of Halodule. So it looks like these more less monotypic seagrass communities end up having a higher Blanc K-score than a monotypic like Thalassia bed or Halodule bed. And I thought that was kind of an interesting descriptive result of the analysis. This is where I had room to put the definition of the Blanc K-score, so this is where it is. But you can see that they range from 0 to 5 and that they just basically estimate a percent cover within the quadrant there. Next slide, please. This is a PCA of those same data. So now we're just ordinating those same data. And basically what this says is sites with high frequency of occurrence of Halodule tended to be different and ordinated different from sites with Thalassia or Syringodium, and that the sites with the rupia or a high frequency of actually no vegetation were separated themselves from the rest of the group. So the plot on the right are these 4 stations up in the top left-hand corner. These are sites that had either a high percentage of rupia or a high percentage of really no seagrass in them. And then the rest of the sites kind of line up on a gradient from the lower left quadrant of the PCA, which is more Halodule dominated sites, to the upper right quadrant, which are more Thalassia and Syringodium dominated sites. The next slide, please. Okay, this is a plot of the distribution of the change in total Blanc K-score. So now we're looking at taking all of the sites across the entire study area, calculating the change from, say, 2004 and 2005, and plotting that difference, and plotting all the distributions of differences. And the question we're asking here is, were there years where all of the sites gained in Blanc K-scores, or all of the sites lost in Blanc K-scores? And the stars represent those years in which there was a statistically significant increase or decrease overall across the whole study area in the average Blanc K score. So 2006, 2007, and 2009 look like good years for seagrass percent coverage. 2012 looked like overall not such a great year. 2014 was again a pretty good year. 2016 not such a great year, and then it's been stable, pretty stable since then over the last 4 years. If you're just lumping all this stuff together, there is a caveat here in that these Blanc K-scores are averaged across all of the stations within a transect. So each site gets one number for each year, which is just the average Blanc K-score. And I'm going to tell you why I think that's not really the best approach when we get to the statistical modeling stuff. Next slide, please. These are the same distribution plots, but they're for each individual strata now. So we're looking at Estero Bay. So the line actually connects the median value of the box plots, but it kind of shows you the general trend of the Blanc K-scores within each stratum. So in Estero Bay, and they didn't start actually collecting data until 2006. We can't do the change analysis until 2007. And so this actually starts in 2007, but you can see that the Blanc K-scores were higher in, say, 2007 to 2011, and then started dropping off until about 2016. Then we had a little bump and then got killed again in 2019. So some of these strata are pretty stable over time, and some of them are increasing over time, and some of them have kind of a parabolic shape. They're all kind of a little different, and that's one of the conclusions of this analysis, is there really is no one size fits all when you're looking at these 58 sites. But there are definitely differences among all these strata in terms of their time series trajectories. Next slide, please. This is another way of looking at each site. And so what we did was we took the change for each year-to-year change in Blanc K-score, and then we just summed it. And we said, okay, over the whole time series, what was the largest cumulative change, either negative or positive? And so going from the top of the plot here, and this starts in 2007 because we want to put everything on the same footing between Estero Bay and the rest of the Charlotte Harbor. There are some sites that cumulatively lost, Blanc K scores, lost percent cover over time, but it was less than half of the total number of sites. There were actually more sites that had either, stable for sure or gaining percent cover estimates if you look at the data in this way. So it wasn't over the entire time series, it wasn't evident that we had this crash across the entire study area of seagrass. The plot on the right is really just looking at the difference between 2004 and 2000. If we did this same analysis starting in 2004 or starting in 2006, and there were some sites where the change in 2006 was negative, but the cumulative change in 2004 was positive, and so there were some differences there depending upon the years, but for the most part, they were consistent. Next slide, please. This is actually a time series plot of the cumulative change in Blanc K scores. The six sites with the greatest cumulative loss are plotted on the left, and the sites with the greatest cumulative gain are plotted on the right. And so you can see that the Brom Blanc K-score actually for like EBO2 does start to drop pretty precipitously after about 2010. You have a little bit of a spike and then it drops again. There are cases in which, like if you look at EBO3, you can have small losses that kind of accumulate, go all the way, you know, down to like 2016 or whatever, and then you can have a big gain in seagrass in one particular year. And so these aren't kind of monotonic trends, they're more subtle than that. And so each site really kind of deserves its own assessment, but it wasn't the overall objective of this study to look at every particular site and describe each result in detail. Next slide, please. This is just kind of some of the nuances. These are those bubble plots again, and some of the nuances of the data. So if you look on the right, ICW01, you can see that in like 2019, we really lost a lot of seagrass at this particular site as defined by this, the size of the bubble and the frequency of samples with no seagrass present. And so you could have a pretty stable site over time as well. And then you could just get this crash like we've seen in the aerial estimates for East Wall happen, you know, for a particular couple years. And that is hard to model statistically, you know, it's hard to kind of tease that stuff out. But that's really evident by some of these bubble plots. So there's a lot of information in these bubble plots, although they are pretty busy that you can get. That I think they're interesting. If you next slide, please. And just more kind of convolution, but on the right hand side, this is the aerial footage from Swiftmud. And the red is a loss between, I believe it's 2018 and 2020. So you can see these red areas where we really lost a lot of seagrass, particularly on the east wall, but they weren't in the deepest part of the transects. They were more kind of on the shoal, on the ledge there. And if you look on the left-hand plot at the top top panel, these are the species-specific Brom Blanc K-scores. So now we're looking at, in the kind of magenta line, a Thalassia Brom Blanc K-score that was really doing really good, and then just kind of fell off a cliff. And so, but at the same time, you know, we actually had modest little gains in Halodule at that site. So, and the same thing at the one below it. So the total Brom Blanc K-score is an aggregate of these individual scores, but sometimes these individual species can cross over and kind of, you know, obfuscate, I guess, an individual species Brom Blanc K-score as well. Next slide, please. We did look at drift algae occurrence over time, and Estero Bay was one that really stood out as being a high increasing proportion of the number of samples that had drift algae occurrence documented with it, as well as Gasparilla Sound and Pine Island Sound. The other strata did not have a significant trend in drift algae occurrence based on the data. I know that you know, observations of recent increasing drift algae you know, have been kind of alarming in some of those areas, and so sometimes the data always doesn't match your observations, but based on these data, we see 3 strata where we definitely seem to have increasing drift algae occurrence, but some others where it kind of just vacillates back and forth. And drift algae has a nature of kind of coming and going as well, that kind of adds variability to it. Next slide, please. Water quality trends. We use the old methods, the seasonal Kendall Tau. I think that there are, that doesn't mean they're bad methods. But we did use the old seasonal Kendall Tau. We do it a little bit differently. This is the entire period of record trends, so it's not just the last 10 years. And that's something I think I would encourage CHNEP to include if they could, would be more than just the last 10 years. But what stands out is, and Miles actually demonstrated this for one of his sites that he showed, but there's a lot of increasing temperature trends in these areas, as well as a lot of increasing total nitrogen trends in these water bodies, and that's that's a bit unnerving. It's not isolated to just the Charlotte Harbor waters. I've seen this in Sarasota and all along the coast of Southwest Florida, but it's definitely has been occurring over time, and it's concerning. Most of the other trends were kind of varied or declining over time. And as Rick was talking about, a lot of complications associated with this. Next slide, please. This just shows if you were to adjust the total nitrogen distribution over time for salinity, this bottom plot here shows you that even so, if you had an expectation for what the nitrogen should be based on the salinity, which is a function of flows, basically, we have more nitrogen that we would expect, even as a function of salinity, in these last 4 years across the board, across the study area. Next slide, please. The opposite kind of occurs for phosphorus, where in the first couple years of the time series, we had more phosphorus than you would expect, even given the salinity in these areas. And so, the reasons for this are unclear, but they do exist. Next slide, please. I know I'm kind of already running behind. These are individual seagrass trends. So each individual species got an increasing or decreasing trend over time. The kind of bars associated with the water bodies reflect their status with respect to being impaired according to numeric nutrient criteria. But we had a lot of increasing trends in individual species over time, even in areas where we had we're above the numeric nutrient criteria. You got to keep in mind that can be a lag effect associated with these things. So these water bodies pretty recently became impaired, and these are long-term trends in seagrass. So I don't want to deceive anybody by suggesting that higher nutrients are good for seagrasses. In fact, I'm going to tell you that they're not. Next slide, please. I'm going to skip these for the sake of time, but basically we looked at the relationship between flows and water quality, and then flows and seagrass, and then went to the relationship between water quality and seagrass for our statistical modeling. There are obviously relationships between flows and water quality, right? I think everybody knows that. So let's skip to the next one. One of the takeaways here is that higher than average flows tended to knock down the Halodule beds a little bit, not really so much the Thalassia beds that we saw. So most of the relationships that we saw between flows and seagrass were driven by changes in Halodule that were associated with increasing flows, reducing the Halodule Blanc scores. Next slide. And there are, of course, distributions of TN throughout the estuary. This is a wide study area. So we've got low salinity waters in the Peace River, in the mouth of the Peace River, and in the mouth of the Caloosahatchee River. And then we've got sites that are all the way out in Pine Island Sound. But there are these breakpoints in the distribution between total nitrogen and Blanc scores, which is the vertical axis on the box plots along the bottom row of this plot. There are some complications in terms of interpreting this, but one of the nice things about this analysis is it gives you these breakpoints, these values. So 0.66 and 0.87. And one of the interesting things when I did this on a strata level was that those values aligned really well with the numeric nutrient criteria that have been established for these estuarine strata. Next slide, please. Again, I talked about this a little bit, but I think it's really important to remember the hierarchical data structure. So we have a strata, we have individual sites or transects within a strata, and then we have these stations within a site. And one of the ways when I went to analyze this was I wanted to try and retain as much of this individual station information as we could without just averaging across all of the stations within a site. For one thing, you only get an N of 1 for a site in a particular year when you do that. And for another thing, there's a lot of important information at the station level that we need to try and recapture. So next slide, please. This I know is probably a lot, but what this shows is as a time series, each individual station within a site. So if the top left is EBO1, we have 3 stations at that site, and you can just see the variability in the Blanc score, the percent cover scores across, between stations within a site. And so while some like EBO2 might be all trending similarly, if you go down to MCO3, you see the wide variability in the bottom center panel that can exist at a station, at a transect just between stations. And so it's really important, I think, to try and, acknowledge this, because basically you're just calculating an average if you don't take the station information into account. And also because, you're collecting those data, so you should really be looking to analyze those data at the level that you're collecting them. Next slide. So I use general linear mixed effects models. It's really just a way of incorporating that station level information in there. And it allows for hierarchical data analysis. I used a pretty simple method. There are other methods. I don't feel like I got as far as I could have into this analysis. And I think it's really a subject for probably a community of practice for seagrass practitioners to kind of explore the best way to analyze these data. But this is what I use. Next slide. And the results basically suggest that TN has a negative effect on seagrass Blanc scores in several strata. So anything with this dash for an individual strata says it's a statistically significant negative relation. So increasing total nitrogen reduces Blanc scores. Total phosphorus was the same way. Where significant, it was almost always negative. The only exception was Estero Bay. Estero Bay seems to, in my mind, maybe be a little bit P limited. It has very low total phosphorus relative to the rest of the strata. But those were the things that stood out, as well as NO302 or nitrates. They all had negative relationships where significant. Next slide, please. Go ahead. I think you can these are animated, but you can kind of go through these. I feel like I'm running out of time. And just go to the summary slide. Oh, this is another way of looking at it. Yeah, that's another way of looking at it, that I use generalized logit models. So in this way, you can actually compare each level of a Blanc score to no seagrass. But essentially, the same thing came out, where if you see the middle column is TN, negative values where statistically significant, meaning that increased TN reduce the probability of occurrence of a Blanc category score, in the higher levels in Estero Bay. And that's kind of the way to interpret that. Next slide. Go ahead. These are animated. So yeah, the sites basically tend to be non-monotypic. The highest Blanc score sites tend to be non-monotypic. The Halodule seem to be responsible for the stations that had, or the transects that had a loss, a high cumulative loss. There were as many stable or positive trends as there were negative trends. Go ahead. It does seem like, instead of some kind of catastrophic loss of seagrass, that we've kind of, in the early part of the time series was a very wet period. Then we went into an extensive drought where maybe we gained some seagrass. Now we've kind of, seems like we're starting to lose some of that seagrass and kind of, we're almost back at a baseline level. There are exceptions to that though. There are places like Estero Bay where it has been declining for a long time, and it's more concerning than, I don't want to minimize it by saying that, we're just back at a baseline level. There are definitely other things going on, but it doesn't look catastrophic to me from analyzing this data. Go ahead. Increasing nitrogen trends are a problem. Go ahead. Nitrates, nitrate really represents new nitrogen or anthropogenically based nitrogen in my mind to the system. There are exceptions, of course, to that with like fish dying from red tide and all that. But and nitrates were an issue in some strata, not others. Go ahead. Go ahead. Yeah. Yeah, I think, in general, it's a combination of things. But TN and temperature and their synergistic effects. There's a paper that I referenced in the report that really goes into some mesocosm studies and the problems with increasing nitrogen in combination with higher temperatures. And I think that's really something that we have to really watch out for. And it means if we are going to be increasing our temperature, water temperature is going to be increasing, it makes total nitrogen even more of a concern in these waters. Go ahead. I've said that. Yeah. Yeah. Go ahead. Yeah. I mean, that's my conclusion is, basically, it doesn't look catastrophic, but nutrients are definitely associated with declines in Brown Blanc scores, and I think they need to be. We need to do everything we can to reduce nutrients, especially given the fact that our water temperatures seem to be increasing. And I think that's basically about it. Yeah. Yep. So thank you guys. I appreciate the time.
Thank you so much, Mike. This was very, very informative. I know it was a lot of data, but
yeah,
this was very an eye-opening for the seagrass work that they're doing monitoring. Okay, so we were going to open to no discussion only, I guess discussion.
we have
Any
a
question?
couple comments and questions
Yes.
online. So David Sealy asks, Estero Bay is our first aquatic reserve, but is in the worst shape with respect to seagrass. Why are we not doing restoration or developing an action plan? Anyone want to respond to that?
That's probably beyond my bailiwick.
Hey, Mike, this is Mindy. I want to thank you too for taking on this monitoring data and doing the statistical analysis. It's kind of beyond the scope of what we can do. So thank you again for all of that. Dave, I don't know if I can really answer your question. Yeah, like Mike said, we just need to reduce nutrients into the system. And so, I'm not a part of the Estero Bay. What's that group called?
Bay for agency management.
Yeah. So
Agency
maybe
of
that's
agents.
we can tackle there. I don't know. I'm not
Mhm.
over Estero Bay, so I don't have the in-depth knowledge there. Sorry.
Judy says, well done. So passing that along, Mike.
Thank
you. That's pretty much all the questions and comments we have online thus far.
There's one more.
Oh, there is one more?
Was Lyngbia considered a drift algae, and what species are?
Yeah, so drift algae is anything that wasn't rooted into the ground. So the new Caulerpa fastigiata algae, we are actually considering a drift algae along with Lyngbia. So yeah, if it's on the seagrass within our quadrant, we are considering that a drift algae.
Any other species that you want to mention that you would also consider drift algae?
Yeah, any of the reds, Acanthophora, that was pretty common, Gracilaria. Those are the most common species that we found.
And there's a distinction between the drift algae and the filamentous algae that is growing now.
We decided to all count it as a drift algae, even though we know the green filamentous isn't really drifting, but it's still kind of a nuisance algae. not the rooted other algae like the prolifera. So we decided to separate those two. Yeah, that makes sense.
It does seem to break off a lot too.
Yeah,
So it's-
and drift. It can, yeah.
She has a question.
Yeah, just a quick question, and it's somewhat random, but I guess Mike or Mindy. I've been hearing, more and more recently about people's concern about increased boat traffic because of COVID and sales of boats and things like that, and impacts to seagrass through prop scars. And so I'm just curious. I know that that's hard to draw back to long-term declines, but it's certainly one element. So I'm just curious if in the data collection and some of these sampling sites, what degree of boat traffic you saw, if that was something you quantified, and if you made a notation, if you saw very apparent boat or prop scars.
Yeah, we do note, when we see a prop scar along the transect, sometimes our stakes are even hit and you can tell that there was a boat going by. But we did recently contract out updated prop scar mapping throughout the Charlotte Harbor area, and it wasn't as bad as I thought it was going to be, just because we lost seagrass. So we could use the recent aerial imagery that the Southwest Florida Water Management District flew. And so using that, we lost seagrass, especially in Charlotte Harbor. And so it appeared to be less prop scars. So that's a consideration to take. But on Island Sound and like Cape Hayes area still have significant prop scarring problems. And we see boats running around almost every day, probably. So there needs to be better education, and we try. But yeah.
So we do have some additional comments coming in. David says, thanks for the great presentation and report. Mark Walton asks, biologically, is Thalassia prone to crashing? Does it have a higher carbohydrate store that we don't see being depleted under macroalgae?
I could say for Thalassia, we've noticed its decline in areas like southern Matlash House, where it's subjected to the Caloosahatchee River low salinities. We've seen it crash there. Like in one transect, it took like 6 years for it to come back after the 2005 Hurricane Wilma time period. But Thalassia has been there ever since like 2011. And then the Thalassia, we've seen it crash along the east wall just because it was smothered by that Clerpa fastigiata macroalgae. I don't know anything about the carbon storage, sorry.
And then Judy asks or suggests that it would be interesting to look at SAV and algae compared to adding reuse water sources.
Mm.
And then Dr. Douglas asks, Mindy, is your recent prop scar analysis data available? And I would just say we're curious too, because maybe that's something we could put on the water atlas.
Yes, the shape file is definitely available in the map. I was trying to write an introduction to that report about the significance of seagrass and stuff in our area. It's still stuck in our comms department, but I'm hoping soon. When that's out, I'll definitely get, but I can hand out the GIS shape file separately now. Yeah, I'll do that.
Okay. I don't see
This is
anything.
Rick. I have a comment about the nutrient loading to the system. The Charlotte Harbor gets, I don't know how much phosphorus per year, but one of Janicki's reports said it was 2,000 metric tons per year. So maybe as a TMDL, that's about 10 times the phosphorus TMDL for Lake Okeechobee. This phosphorus, a lot of it ends up in the sediments and builds up over time. And the phosphorus along with nitrogen from the sediments can feed benthic algae like the Clerpa. So that Clerpa, if it gets started, can grow over the seagrass wherever it gets started because it has such a large nutrient supply from the sediments. So I think we need to publicize that we need a lower TMDL than Lake Okeechobee. We need to prevent our seagrass from going the same way that Indian River Lagoon, Biscayne-based seagrasses have gone.
Well, I think what you're bringing up too is that, a lot of times the TMDLs they're looking at one nutrient or the other based on, is it quote a phosphorus limited or nitrogen limited system? And there's a lot of science that's been out there a long time, specifically from Dr. Joanne Burkholder, that says it's all about the NP ratio and that these systems can adapt, where if you reduce one without in tandem reducing the other, that these organisms can shift to take advantage of the other, so that you really should be trying to target reducing both simultaneously, but our TMDLs are not usually set up that way. And that is something, and also the stormwater regulation for ERP permitting is also not set up around nutrients per se at this point. And when they've discussed updating those regulations from total suspended solids to nutrients, they have again talked about trying to make freshwater systems focused on phosphorus and saltwater systems on nitrogen, and not looking at both together throughout the whole system. So I think that's just, again, an issue with a disconnect between science and policy and how we need to be approaching nutrients.
Right, Hans Perl is one person who has suggested that you need to set nitrogen and phosphorus limitation standards for estuaries. When he was down here doing research on red tide and Lyngbia or DAPIS. But the point is having lower loading rates of nutrients than we have currently, much lower than we have set for TMDLs is what we need, because we have so much built up in the sediments, and it's going to keep fueling DAPIS blooms and Clerpa blooms. The DAPIS can fix nitrogen from the atmosphere, from the water column, so it doesn't need, cutting back on nitrogen won't affect the DAPIS, the Lyngbia. But the Clerpa has all the phosphorus and nitrogen, especially when it kills organisms underneath the mats, when the oxygen gets taken out from underneath the mats by decomposition from bacteria in the summertime.
Not to cut it out, the comments, but we can move on to the next, unless there's more.
Let me just check one more time.
Yeah,
There was just a comment from Dr. Douglas. He just shared some of the crop scar analysis that FGCU has done in partnership with the Estero Bay Aquatic Preserve, and the link is in the chat if anyone's interested.
okay. Excellent. All righty. So no action items